book is more similar to magazine than water. This is because their semantic similarity makes it possible. And in the same way, you can say the document 1 is more similar to document 2 than document 3, even if there no words in the documents are overlapping. And I compare the chapters of the Taittiriya Samhita using this semantic approach, and the rest of the presentation is also dedicated to explaining this semantic approach, semantic representation. Now, let's take a look at the definition of semantic similarity. What does it mean for words to be similar? A linguist said, "You shall know a word by the company it keeps." That means you can know the meaning of a word by seeing the words surrounding the target word. Now let me give you an example. Imagine again there are 3 words: hot, cold, weather, and they have different grammatical functions. Their part of speech is different, and hot has even the opposite meaning of cold. But according to the above definition, these words are regarded as similar in that they occur in the same context many times. So whenever the term weather is mentioned, then hot and cold are most likely to be mentioned. And yes, now we have figured out the definition of semantic similarity. Now let's see how to represent it. And there is a way by which we can represent documents or texts, which I call vector space model. The term vector space model is usually applied to the vector representation of documents or text, but let me introduce this term in the application to words. And in this vector space model, every word is represented as a vector, and a vector has both direction and magnitude, and usually has 2 or more dimensions, as you see in the example. These vectors have 3 components, or 3 dimensions, you can also say. And according to the difference of the meanings, the components change. Now I here introduce 2 ways to methods to create word vectors. One is topic modeling. And in topic modeling, there are several methods. For instance, LDA. LDA stands for latent delete allocation, and LSA stands for latent semantic analysis. And their names indicate they serve to detect the latent or hidden topics that you cannot directly find in the documents. And in this topic modeling, a component of the vector is nothing but the topic. But I do not use this topic modeling because it's difficult to tune, it's difficult to adjust. For pre-processing, one has to split documents into small portions so that every portion contains the same number of topics. Instead, I decided to use Word2Vec, in which one can create a model without splitting training corpus. And Word2Vec was created in 2013 by a researcher team led by Thomas Mikolov at Google, and it is based on the neural network model. And this is a paper in which Word2Vec was introduced for the first time. And now I'm going to introduce some of the important parameters for Word2Vec. Actually, I wanted to explain the entire algorithm of Word2Vec, but it would take time. So let me just skip the details about the vector generation process of Word2Vec. In the first place, I need a text corpus as a training corpus. And the second important parameter is a choice as an option between continuous backwards and a skipgram. And Word2Vec is based on conditional probability, and this option is about how to train a corpus. And in Word2Vec, a model is trained based on conditional probability. And in the training process of continuous backwards, the target word is predicted given the context words. And on the other hand, in the training process of skipgram model, the context words are predicted given the target word. And it is usually said that skipgram works better than continuous backwards. So I adapt skipgram model for my text analysis. And number of windows is nothing but the range of context. And let me give you again an example sentence. I eat an apple, an orange, and a banana. If you take orange as the target word and the number of windows set as 5, then the 4 words surrounding the target word orange are chosen as its context. And the Python library of Word2Vec gives 5 as a default, and I just simply take this default. And as for the rest of the parameters, I just simply take their default. The number of hidden layers is here means the number of components of a vector, and the default is 100. And the last parameter that I introduced here is the minimum frequency. That is, one ignores words with total frequency lower than this value. And so by this minimum frequency, 2 less frequent words are ignored or removed, and the default value is 5. As a result of the calculation, you get word vectors, and given the word vectors created by Word2Vec, the following vector calculations are possible. Vector of a king minus vector of man plus vector of woman is equal to the vector of queen, and so on and so on. And it looks like a magic, but this is one of the important characteristics of Word2Vec, or of the characteristics of the vectors created by Word2Vec. And then you might ask a question, how to measure the similarity between vectors, or how to compare the two word vectors or meaning of two words. And there are many methods, but one of the most used measures in the field of natural language processing is cosine similarity, and it is not only intuitively understandable but also works quite well. But and in the formula, AB stand for different two water vectors, and AI and BI are their components. The cosine theta is calculated by dividing the inner product of the two water vectors by a multiplication of the length of the two vectors. Now in this slide, I give you some visual intuition. Since cosine theta has a range between -1 and +1, the cosine similarity, the similarity of two vectors is represented in the same range between -1 and +1. And as you see in the right figure, if the two vectors are facing in the same direction, then the angle made by the two vectors is smaller, and the cosine theta is getting closer to 1. That indicates that two water vectors are similar. That means that the meanings of the two words are similar. On the other hand, if the two vectors are facing in the opposite direction, then the angle made by the two water vectors is bigger, and the cosine theta is getting closer to -1. That indicates they are opposite. The two water vectors are opposite. And the next question that you might ask is how to compare sentences or chapters, or how to create composite vectors, or sentence vectors or chapter vectors, and how to compare sentences or chapters with cosine similarity. It's quite simple, but there are many methods to create composite vectors. But the way that I introduce now is I would say one of the simplest ways. One can create composite vectors just by adding water vectors, and after adding water vectors, the sum of the water vectors should be divided by the number of water vectors. Otherwise, the magnitude of a vector created from a long sentence would be much larger than that of a small sentence. And this can be applied to a document with any size. Now, this is the last section. And in this last section, I'm going to show you how the entire process of the text analysis is carried out, and after that I show you the results. In the first step, the text corpus should be cleaned, and I use the text corpus of Dr. Helvig that you can find on his GitHub page. And his text corpus contains not only Vedic texts, but also some other Sanskrit literatures. And there are some other things to do in this phase. And I'm going to touch upon these points in the next slides. And the second, I train a model using the clean corpus, and I use the model to create word vectors in Taitiya Sankhya. So in this phase, I so to say allocate word vectors to the words appearing in the Taitiya Sankhya. And next, I create a composite vectors for each chapter by adding word vectors. And finally, I compare chapter vectors with cosine similarity. Now, I'm going to discuss some points that I should keep in mind, that I should pay attention to in the first phase. To begin with, removing stop words. Stop words are almost identical to function words that occur too frequently and have less information than content words, such as is, and, then, and so on in English. And it is not always necessary to remove stop words, but in our analysis, they just give rise to noises in the semantic representation. So they should be removed. And in this connection, I have to remind you that two less frequent words are also removed by the minimum frequency, which is one of the most important parameters of word-to-vec. And by this removing stop words, two frequent words are also removed. And in this example sentence, mano marta abhi durhan tanunam indra girvanaha. Mano abhi are particles or pronouns which are less informative, which are stop words, so they should be removed. Next, stemming and lemmatization. As you may know, in Sanskrit, many of grammatical features are preserved in case endings or in verb conjugations. And to cancel the inflected forms is called lemmatization. On the other hand, stemming is the process of reducing different forms to its stem or its root. For the sake of understanding, I give you an example in English. Beauty, beautiful, beautifully. They have different part of speech, but they are all derived from the same root or stem. But I'm not sure if there is such a thing in English. But in Sanskrit there is. In the case of Sanskrit, for instance, gati, gamanam, gamakaha, gachati, gamyate, and so on. Even though their part of speech is different, even though they have grammatically different functions, they are all derived from the same root, gum. But since stem is not registered in the corpus that I used, and I'm not sure if stemming is appropriate in this case, so I just applied lemmatization to my text analysis. In this example sentence, I get rid of all the grammatical features in order to identify different forms at the same word. Otherwise, for instance, tanunam, which is genitive plural of tanu, would be distinguished from tanu, even though tanunam is inflected from tanu. So the inflected forms should be cancelled. And the last thing that I want to point out here is backwards. And this is a little bit overlapping with stopwords and lemmatization. But under this concept, a text is regarded as a back, which in which words have any words doesn't have do not have any order, and grammatical features and negation and so on are not taken into account. So I would say, unfortunately, it's hard to distinguish mantras from prose given using this my approach. And this is the corpus that I used, and the format of the corpus is called Konlu, which is supported by universal dependencies. And universal dependencies is a framework of grammatical annotations across many different natural languages. And for in the corpus, what I need for training a model is lemma. And the chapters which are to be compared are also tagged here. And this is the corpus information. In the training corpus, there are more than 6,000 texts, and the average number of sentences in a text is about 100, and the average number of tokens in a sentence is 5.57. And the corpus of Tetir Sankta, there are 32 chapters in total, and the average number of sentences in the chapter is 26, and the average number of tokens in a sentence is less than 5. And as you may notice, the average number of tokens in a sentence, or the average number of sentences in a chapter is quite small. So it should be called paragraph instead of chapter, but let me keep calling it chapter. Last but not least, this is the results. And the color of each cell in this heat map stands for the similarity, the semantic similarity between two chapters. And for the sake of the explanation, let's take a look at this black cell. The black color indicates that the two chapters 452 and 1113 are not similar, and they have the two chapters have low cosine similarity. Their cosine similarity is less than 0.6. On the other hand, the diagonal line is white. That indicates that chapters on these white lines are have high cosine similarity, and their chapters are similar to themselves because they are compared to themselves on these white cells, and not surprisingly, they are similar to themselves. And the last point I want to point out before taking a look at each single issue is that the number of chapters are discrete, so not continuous. So there are missing other missing chapters. Now let's take a look at each single issue. The most conspicuous point is the this dark line of chapter 452 that indicates that chapter 452 is not similar to the other chapters. And I investigate the codes, and I found out that in that chapter there are many, so to say, salutation phrases such as Namah Shivaya, which means saluting Shiva or bowing to Shiva. But take a look at this cell of 451. This chapter has slightly lighter color compared to the other chapters or other cells on the same line. That indicates that chapter 451 is relatively similar to the chapter 452. And I also checked the codes and found out that in that chapter too, there are many Namo sentences, Namo phrases. And the second point that you might notice is this slightly darker line of the 1113. I also checked the codes, and the chapter 1113 has slightly darker color because this chapter has only 2 sentences. So I guess the amount of tokens is not enough to bring about the proper result. The last point that I want to point out in this heat map is that the chapter 111 and 1112 have slightly lighter color compared to the other chapters here. This area has slightly lighter color that indicates the chapters 111 to 1112 have they are similar to each other. And there might be some other interesting point to be indicated from this heat map, but for now, that's all for my presentation. I have no summary slide. Thank you for listening.
Thank you. Thank you for your interesting presentation. Does anyone have comment? Yes, please. Yes, Sebastian.
Yes. Thank you very much. I hope you can hear me. Yeah.
Yes.
Thank you very much for the great presentation. We also use the word vector model for the Sanskrit database at the Buddha Nexus. So
Okay.
I think the methodology is quite similar in certain
yes,
ways.
I actually I heard your presentation at the day, the day before yesterday. Right?
Oh, nice.
Yeah, yes.
Yeah. Yes. There's one question. The first question I have, since I noticed that when accumulating word vectors and taking the average of them in order to get like sentence representations or representations of longer phrases, I observed the tendency that the longer the phrase get, the more similar the vectors are. So, and one way to tackle that in our case was to limit and only compare phrases with the same length. So we always looked at phrases that have a length, for example, of 7 tokens or 10 tokens. I wonder what your strategy was. Did you also limit yourself to only look at the same lengths, or?
No. Thank you for comments. I have not taking into account such a point, I perhaps in the next analysis I can consider about your point. Yeah, thank you. I just applied the simplest method, and as I said, there are many other methods, and as you said, I perhaps I should limit the length of the um, chapters when I compare vectors or sentences. Yes, yeah, it's a good point. Thank you very much.
It's just from my experience, as long as you compare units that have the same length, the average of word vectors is quite reliable. But as soon as you have something which has 5 tokens and something which has 10 tokens, then it gets more difficult. Yeah, and the larger the difference is. Yeah. So I just wondered how you approach this problem.
Yeah, no, it's as I said, I didn't consider about this issue. Thank you very much.
Yes, and one more small thing. I don't know if you considered this yet. So there are also a little bit more recent developments, like context-aware models that create sentence representations based on the context. I think BERT, for example, is a very famously received paper, and there are also models to calculate sentence vectors based on that. I think one very recent publication is called Sentence Transformers.
Okay.
These are highly, resource-intensive models and applications. But I think maybe one can also try to work with that, because in that case, I think the length of the phrases that are compared don't play such a big role anymore, because the mechanics is a little bit different. Yeah.
Could you send me a link to the paper, or?
Yeah, I will write you an email later, of course. No problem.
Thank you.
No problem.
Thank you very much.
Yeah. Okay.
Thank you very
okay.
much.
That's it. Yeah. Okay.
Thank you. And Tyler, you have a question? 2 questions.
Yes. Okay.
Yes.
Thank you, Yuki, for the talk. So I appreciated Sebastian's comments and questions. Some of them are what I also was curious about. Let me ask you about the stemming. So I saw when you showed the data that you were using on the Conlu, I think it's how you pronounce it, format, that there was no stemming data there, just the root.
No.
And so what I didn't quite understand was when you say that you cancel out the inflections, do you actually just use the root, or?
No, I since stem is not registered in the corpus, so I just applied lemmatization. And so to cancel the inflected form means that I just simply apply lemmatization, not excluding stemming.
Okay, so I would imagine there's maybe 3 options: using the root, using the stem if it's provided, which, by the way, I feel like I actually have seen the stem information is in the DCS, but in a different kind of release of the data. So we can talk about that later, whether that would be helpful.
Okay. Yeah.
But the third, you're saying that you're using a lemmatizer, or you're doing lemmatization.
No.
What tool did you use to do this?
No. I didn't use any lemmatizer. I just simply let me just show you the corpus that I used here. In the corpus of Dr. Helbig, you can find lemmas.
These are the lemmas, I see.
Yeah, these are the lemmas, and I used the lemmas here in the corpus.
Okay, so it's mostly the root, but in certain cases, a different citation convention, like tvud, is not a root, but is the citation form.
Yeah.
I see. Okay. And I can defer if other people have a question. Otherwise, I could ask one short one. But I will wait to see if anyone else wants to ask. Thank you, Yuki.
Welcome.
Any other comment?
Okay, a very small, fun comment. Yuki, I think it will be very nice if at some point you can show some examples of the simple math, the semantic math that you gave an example of. So I've never seen this yet, but if anyone would produce, well, when you have these little equations like king minus man plus woman equals
okay,
queen.
that one, yeah.
Yes, if as a little project, maybe you can try to come up with some real life examples from your data if this works. This would be nice someday.
Okay. Yes, I'll do it. Thank you.
I have a small question. How do you deal metaphoric meaning of word, or it's
You mean metaphoric? Or which one do you mean again?
You evaluate the meaning of words, no? So the opposite or similar.
Ah, yes.
So if a word has a metaphoric meaning,
It's a good question. The meaning of a word is determined, as I said, the co-occurrence. So I would say it's difficult to take into consideration the metaphoric meanings. So, but somehow they are they might be included if there are metaphoric usages in words in the corpus, in the training corpus. But I would say the metaphoric meaning is basically it is not taken into account in this.
so time is now over. Thank you very much.
Thank you.
Thank you.